Yes, thank you so much for the introduction. Thanks for the invitation to Vienna. It's very nice to be here at this workshop. So in this talk, I will speak about several joint works with Moritz Kassmann. Most of them we completed, I think, more than 2 years ago. But there's some recent paper with Naian and Liao that I will also mention towards the second half of my talk. And yeah, as you can see from the title, they all deal with non-local equations and with time-dependent non-local equations, and in particular Harnack inequalities. So as you know, I guess in the last 20 years, there's been a lot of effort in the community to somehow understand in what way non-locality enters or changes the behavior of regularity theory for PDEs. And this is pretty much what this talk is also going to be about. However, it turns out, and this was a bit surprising to us, that when you consider time-dependent non-local problems, they are much more difficult to treat, and also some purely non-local things happen. And this is what I want to focus on in this talk. And so I want to explain some of these phenomena and also explain how in the end we were able to get these Harnack inequalities, which was something that we struggled with proving for quite a while. And then before I start, let me also mention that basically everything that I mentioned today will be about linear equations, linear non-local equations. And a lot of things are still open for the nonlinear case. So maybe some of you are interested in nonlinear versions of these results. If you are, then you can approach me and we can discuss about that. Okay, so to warm up, I want to briefly explain what is the local theory. I guess you're all very familiar with this, so I'll try to be fast. So the situation is as follows, okay? We consider a parabolic PDE with the second order operator in divergence form, like this one, not like before lunch where we had equations in non-divergence form. These are operators that are in divergence form, so they come from energies that are minimized. And then you have here coefficient matrices Aij that we just assume to be bounded from above and below. So you have boundedness and you have uniform ellipticity, but we don't assume any regularity on the coefficients. Okay, and then a very well-known result that I guess everyone here in this room has seen is that solutions to this equation are always Hölder continuous, yeah, with a small Hölder exponent. And that's a surprising result because we did not assume any regularity on the coefficients. And in this parabolic case, this was proved by Nash and Moser, but of course, one also has to mention the name DeGeorgi here, at least in the elliptic framework, where this result was basically the missing piece in the resolution of Hilbert's 19th problem in the 1950s. Okay, so this result is very well known. Also, the second result that I want to state here is very well known. So in the same class of operators, solutions that are non-negative also satisfy a Harnack inequality like this one. Yeah? So you can always compare the supremum of the solution in a certain cylinder. You can bound it from above by the infimum of the solution, where here you have to take the infimum at later time. There's always a gap between the time where you take the supremum and the infimum. And where this Harnack inequality was proved by Moser, so it's a different approach to this Hölder estimate from my previous slide. And this Harnack inequality is also very, very well known and very powerful because it has many applications. For instance, you can use it to prove estimates for the fundamental solution to the Cauchy problem that is associated with this equation. And you can say something about the corresponding stochastic process and how the transition density looks like as well in this linear scenario. So what I want to discuss in my talk is in what way these results remain true in the non-local scenario. Okay, this is going to be the goal of my talk. And as I said before, a lot of research has already been put into these kind of questions. But in the parabolic case, which is what I just presented to you, several questions have remained open. And I want to explain today how we were able to overcome these problems and also in what way results might be different from the ones here in the non-local case. Okay, so I have prepared a very basic slide here just to give you like a brief introduction into non-local operators. We've seen them already during this conference, but I just want to emphasize 1 or 2 points to give you like the same perspective on these problems as the one that I have. So whenever I say a non-local equation or non-local operator, then I will usually speak about equations that are modeled upon or driven by the fractional Laplacian, or operators that behave like the fractional Laplacian. So this is what I define here on this slide. There are several definitions of the fractional Laplacian. I just chose these 2. So the second one tells you that you can view this fractional Laplacian as a Fourier multiplier operator. Yeah? So you have a fractional order of differentiability here, 2s instead of 2. So in a sense, you interpolate between the actual Laplacian and the identity, and it's an interesting question already to see, to understand in what way fractional order of differentiability influences regularity of PDEs. But what you do not see from the second definition is that this fractional order of differentiability actually leads to non-locality, and this is what you can see in this first definition here. So when you want to evaluate the fractional Laplacian at a point x, actually what you do is you need to evaluate this integral here, and this takes into account the values of the solution u, of the function u, everywhere in space. So you need to know the function everywhere, even if you want to compute the operator just at the point x. And this non-locality leads to interesting questions. Namely, now imagine that you solve an equation like fractional Laplacian u equals 0 in a domain, then a solution might have very weird behavior far away from the domain, but this still influences the value of the operator at x, so it might be that the solution also has to have weird behavior inside, and then maybe regularity properties fail. Yeah, so we need to, and we want to understand how these long-range interactions influence regularity theory. That's the main driving question. And then, as I said, we want to develop a non-local analog of this de Giorgi-Nash-Moser type theory. So what we do is, like in the local case, where you put here a coefficient matrix, you also want to put coefficients for your non-local equation, and there are several ways to do this. But when you want to have a divergence from operator in the end that comes from the minimization of an energy, then what you do is you replace this kernel here by a function k that behaves from above and from below like the kernel of the fractional Laplacian. Yeah, and these upper and lower bounds, they basically correspond to the boundedness and uniform ellipticity of this matrix. Yeah, and this is something that many people in the community usually assume as the natural counterpart here. Okay, and then it's, I guess, now very clear what I want to explain. I want to explain in what way Hölder regularity estimates and Harnack inequalities hold true for this red operator here when you do it parabolic. Okay, this is the goal of the talk. And as I said before, many people have studied these kind of questions. In the elliptic case, basically everything is understood. And in the parabolic case, several questions remained open. And this is not only because people were too lazy to do it, but there are really structural problems here. And actually, it turns out, I can spoiler you already, that not all the results from the first slide will be true in the non-local case. There will be exceptions, and that come precisely from this parabolic nature that I will discuss. Just quickly, 3 keywords. Why are we actually interested in these operators? Well, there are several approaches that can motivate you. One is from probability. Yeah, so you know that that the Laplacian is the generator of Brownian motion, which is a process that has continuous sample paths. And then these non-local operators, like the fractional Laplacian, they generate jump processes. Yeah, and they are also a very important object in probability theory. And to understand them better, we develop this theory from an analytic point of view. Yeah, you can also understand or try to understand in what way a non-local version of Hilbert's 19th problem holds true in the non-local case. That would be another motivation. But what drives my interest recently very much is the Boltzmann equation, yeah, which is an equation from statistical mechanics. It's a kinetic equation, so it's even more general, even more complicated than parabolic equations in a sense. But these ones are really non-local in the velocity variable, and the operators that you encounter are precisely these ones. Yeah, so we want to understand maybe better this equation, and then what I'm explaining today is like a toy model in a certain sense. Okay, so I want to quickly explain now what is known in the elliptic case and give you like at least a little glimpse into the ideas of the proof so that you can follow later and understand better what is difficult in the parabolic case, but I won't go into too much detail, and I also think that many people in the audience, they know this theory, at least in the local case, very well. So I will focus on what changes when you have a non-local equation, okay? So what you can prove, and this is known for many years, like 15, 16 years ago by Moritz Kassmann, is that when you look at an elliptic equation with such a non-local operator, then you can prove a weak Harnack inequality like this one. Yeah, you can bound the L1 norm by the infimum, and this is also true in the local case, of course, but here it turns out that the non-locality enters because you need to assume that your solution is non-negative everywhere in space. Yeah, in the local case, you assume it only in the solution domain. For non-local equations, it might happen that your solution is very bad outside, as I explained before, and then this Harnack inequality fails. So you need to control it at least from one side in order to have these local estimates. And then you can also prove Hölder estimates like this one. So also here, without any assumption on the coefficients, solutions will always be Hölder continuous, but you need to assume here that the solution is globally bounded. Yeah, not just bounded in the solution domain, but globally bounded. Okay, and this you can prove using an adaptation of Moser's iteration technique. Yeah, so I won't explain in more detail. Just the key message here is that you can adapt the local techniques if you take into account the non-locality in the right way. And then it becomes more interesting when you're thinking about whether every solution is actually locally bounded. Okay, so here the non-locality enters in a much more crucial way. So for subsolutions in the local case, you can always prove that the supremum is bounded by the L1 norm. This is a very standard thing. You can prove it using the Georgi iteration. And also in the non-local framework, you can prove something like this. But it turns out that you always have to add some non-local quantity in these estimates. Yeah, and these non-local quantities, we've seen them already, for example, yesterday. They are usually called tail terms in the community. So what they do is they are basically weighted L1 norms in the full space. Yeah, so what you have is when you solve an equation in a ball with radius r, then you can control the supremum, or in a ball with radius 2r, let's say, then you can control the supremum in the ball with radius r by the L1 norm in the larger ball, but you also need to take into account everything that is outside, and you also need to measure it in an L1 sense, but you can put this weight here, which means that basically the further away you move from your ball, the less important the values of your solution get. And the weight is precisely the one that has the same asymptotic behavior as this kernel of the fractional Laplacian. Yeah, so you have a global quantity here. It's still in L1, but you cannot get rid of this tail term in the estimate. If you don't have it, this estimate is false. Okay, and then one more feature of this estimate, I just want to highlight this. So what you can do here is you can always interpolate in a sense between the local quantity and the non-local quantity, because you can see here there's a small delta in front. Yeah, so you can somehow make the non-local quantity as small as you like if you put more weight to the local quantity. Yeah, this is a very interesting or important feature. Okay, and then if you want to get a Harnack inequality, you combine this estimate with the weak Harnack from the previous slide, and then you get supremum bounded by infimum, but you still have this tail term floating around. And the last question is if you can get rid of this tail term. And this is also something that was found to work already 10 years ago. So there's this paper by Di Castro, Cusi, and Palatucci, which says that you can always estimate this tail term, which was this integral outside the solution domain. You can always estimate it by the largest point of your solution inside the ball. Yeah? So this estimate is the one I'm talking about. And this is a purely non-local estimate. In a sense, it's like a reverse maximum principle. Yeah? Because when you solve an equation in a ball, then you can also just put some boundary data that you prescribe in the exterior. And then what this estimate says is that you can basically control the exterior data that you can prescribe by the values of your solution inside the ball. Yeah, it's somehow a reverse maximum principle. It's a purely non-local thing. And once you have this, you can prove the Harnack inequality, because when you estimate the tail by the supremum, then you can basically absorb the supremum to the other side because you have this small delta here. This is the standard iteration argument. And then you have the Harnack inequality. Okay, so I don't want to say anything more about the elliptic theory. So the takeaway message is, if you do it in the right way, if you control these tail terms, then you can basically produce the same results. You need to take into account the non-locality sometimes throughout the way, but this has been established in the last 15 to 10 years. So this slide is just for everyone to get like a little intuition of how it works. I promise you I won't spend too much time on this. I just want to give you an idea of what it means to be a weak solution to a non-local equation and say why these tail terms appear. Okay, so if you have an elliptic non-local equation and you want to interpret this in the weak sense, if you do it in the classical way, you write down the corresponding energy, and this looks like this. Yeah, this is a double integral, and instead of having here gradient of u times gradient of phi, you have differences. Yeah, instead of derivatives, you have differences, and you integrate in the full space because it's a non-local operator. Yeah, but then if you want to prove, for example, this local boundedness estimate, you can do a De Giorgi iteration or a Moser iteration, pretty similar to the local case. You take test functions phi here that are basically a cutoff function by times the solution itself. And when you plug this in here, then you get this expression. And then you might want to use the chain rule, but because it's non-local, you cannot really do it. But you can still derive some algebraic identities like this, and then you can still get a Katsopoli inequality. So this first term here if you use that your function tau is 1 in the ball, then this integrated will give you the HS semi-norm, and the other term, I just copied it here. And now you see, and that's very important, why non-locality enters. Well, because here, this integral here, although there's this cutoff function tau here, which has compact support, you will still need to evaluate the function u outside the solution ball at some time. Yeah? So when you estimate this quantity, you will get a local quantity, but automatically you will also get an integral over the complement of the domain. And there's no way to get rid of that. Okay? So you don't need to follow this in all detail. The only takeaway message is that when you just test your solution with a test function that is compactly supported, you will still get these global integrals that you need to control in your iteration process. Okay? So there's no way of avoiding them. But once you have such an estimate, you can still use a Sobolev inequality and gain some integrability here, like you usually do in a de Giorgi iteration argument. Yeah? And then you just need to take into account these tail terms and iterate them, and then you can prove these estimates. Okay? So I know I was pretty fast here, so that's not a problem. The takeaway message, as I said, is you can do it if you do it in the right way, if you replace chain rule by these algebraic identities, and if you can control these tails. Okay? That's everything that you need to know for the rest of the talk. Okay, so now I want to discuss what changes in the parabolic framework. And as I said, I want to focus on the purely time-dependent, on the purely parabolic phenomena that occur. Okay, so now we consider a similar operator, again, comparability with the fractional Laplacian, and it can now depend on time. Okay, and then we want to develop a similar theory for this parabolic, for this time-dependent problem. Okay, and now I put here a lot of references of people who have worked on these questions, and I'm cheating here a little bit because there are basically two classes of papers in here. So there are several papers who are really considering this equation and proving some theory like this one for this linear equation, but there are also many papers in here that consider generalizations of this equation to nonlinear problems, for example, or double phase or porous medium, things like that. Yeah, so there are many people interested in these kind of equations. I will only focus on this linear case because even in this linear case, there were open questions, and in this recent paper, we answered them, and this is what I want to explain today. Okay? All right, so what is analogous to the elliptic case? Let me start with that. So when you take such a parabolic non-local equation, you can still prove a weak Harnack inequality and a Hölder estimate. Yeah, this is not so different, not so difficult, and not so different from the elliptic case. Yeah, so in a sense, once you have this Harnack, this weak Harnack inequality for an elliptic equation, and you understand how in the local case you can go from elliptic to parabolic, you can basically merge the two ideas, and then you can get a control of the L1 norm in time and space by the infimum in time and space. There's no real new idea needed here. The same is for the Hölder estimate. So every bounded solution, globally bounded solution, you can prove that it's Hölder continuous in the same way. But what I want to understand today, and this is what I wrote here, is whether every weak solution is locally bounded. Yeah, this is something that doesn't follow from this estimate. Also, whether every weak solution is Hölder continuous. Also, this doesn't follow from this estimate because here we are assuming that it's globally bounded. Yeah, not every weak solution is globally bounded. So it's still open here whether every weak solution is Hölder continuous. And in particular, we want to know whether we can prove an actual Harnack inequality where here you replace the integral by the supremum. Okay, these are the three questions I want to address. And all of them have been open until very recently. Okay, so these are the only ones, the only results that were available. So what is now the first step if you want to prove these things? Well, usually first you want to prove that every weak solution is locally bounded. Okay, that's usually the first thing. And when you do this, and many people have tried, including myself, and then what you get when you naively sort of adapt the elliptic case, make it time dependent, you will end up with estimates like this one. Okay? So you know, I guess from the elliptic case and from the local case, again, you can bound the supremum by the L1 norm, but then you get these tail terms in your estimates. And when you do this, you have to ask yourself, in what way does the tail term enter in the estimate? And this tail term, if I remember you, how it looked like, this was a function that was basically the integral over the complement of the ball of your solution times this kernel. But now if your solution depends on time, then also this tail term will be a function that depends on time, and therefore you need to put a certain norm here of this function in time, a certain LP norm. And when you just adapt the classical arguments from the elliptic case, like in a naive way, what you will get is the infinity norm of this tail term. And of course, this is not always finite. You might just solve the Dirichlet problem with some boundary data here that does not have finite supremum tail. You just put some boundary data that doesn't satisfy it. It's a weak solution, so well, then this estimate doesn't tell you anything because the right-hand side is infinite. So this is not what you would like. So in particular, if you want to prove a Harnack inequality, this does not get you far because this is an infinite quantity. You cannot hope to bound it by something local because it might be infinite. So you need to replace it. There's no way that this estimate is ever good enough. And then you might ask, okay, what is the natural quantity that you should put here? And it turns out that the only quantity that qualifies for being put here is the tail term that is L1 in time. Because when you think about weak solutions, what you do in the parabolic case is you take the energy and you integrate the energy, right? And this energy, as I told you before, it always contains these tail terms. So when you integrate the energy, then this is the only thing that is finite, the L1 tail. So you need to put it here. But for this, the techniques were not there. So you really need to work hard to get this L1 tail here. Okay, so now it gets a little bit technical, of course, because I'm talking here about certain norms of tails. I want to get very simple now again, and I want to tell you why it's actually challenging to put this L1 tail here. It's not just, okay, you improve some exponent. It's really challenging because it's the critical case. And this is what I want to convince you of now on this slide. So look at this toy model here. So you just solve the fractional heat equation in a time interval times the ball. Okay, let's just solve this equation. And then I told you that the tail term is basically an integral over the complement of the ball. So what you might do is, let's just multiply the solution by an indicator function in the ball. You just cut it off, call this function v, and check what equation is solved by v. I just ignore the tail terms. When I do this, then I get an error term on the right-hand side. And this error term is just the application of the fraction Laplacian, my operator, to the thing that I cut off. And when I do this, if you remember how the fraction Laplacian looked like, you basically get the tail term here with radius 1. Well, and if I now want to assume that this is an L1 in time and L infinity in space, and you know something about these inhomogeneous parabolic equations, you will realize that this right-hand side, the space here, is the scaling critical space. Okay? What it means is that when you zoom into your solution or zoom out of your solution, this term will always have the same size. It will not become smaller or larger. You cannot treat it by perturbative arguments. It's the critical case. You need new ideas in order to treat this term because you cannot argue it away. It's not accessible to perturbative arguments. And the second thing, and that's of course related to this first observation, is that actually we found that when you have an equation like this, where you prescribe boundary data that is only L1, that the tail is only L1, then this is not necessarily Hölder continuous. Okay? So we construct in our paper a counterexample of a weak solution where you prescribe boundary data that is in L1 and it's not Hölder continuous. And this is something that does not happen in the local case. In the local case, every weak solution is Hölder continuous. Here it's not true anymore. Okay? And this is in a sense a purely non-local phenomenon. And I have a slide here that explains the counterexample. I don't want to go into detail because it's a bit technical, but just for those who are interested, so what you do is you can look at this picture here. So you solve an equation in a time interval times the ball, and then you put certain exterior data. And the exterior data that you put is 0 up to time 0, and then for time 0 to 1, you put some exterior data like a function h, which I define here, log t to the minus 2. And then in this box, you also add the derivative of h. Like you put a non-local boundary condition here. And then it turns out that you can choose the delta very small, and then the function g will actually be a subsolution to your fractional heat equation. Okay? And then what it means is that by the maximum principle, here your solution will be 0. And here, your solution will be bigger than the boundary condition because G was the subsolution. And then the function g is just h, and this is log t to the -2, so it's not Hölder continuous. And then u, because it's larger, can also not be Hölder continuous. Yeah, and this boundary data is chosen in such a way that the tail is in L1, but it's not of higher integrability. So it's a counterexample. You cannot prove Hölder regularity for solutions that have L1 tails only. Okay. So that was the phenomenon. So I hope I convinced you that it's difficult to treat these L1 tails because things break down, they are scaling critical, but these are the ones that you need to get in your estimates. Yeah? Otherwise you cannot prove Harnack. So what we proved, and this is the first new result that I'm showing you, is that actually you can put the L1 tails. Yeah? You can put them in such a local boundedness estimate. It's exactly the quantity that is finite. It's exactly what you dream of. But if I hadn't told you the things from before, it would be much more boring. Yeah? So it's really, it's a mess to get this, to get these terms in your estimates. Okay, and of course this implies that weak solutions are always locally bounded. Yeah, they're always locally bounded, but they might not be Hölder continuous. Okay. So how do you get these terms here? I prepared like a little sketch of the proof. I just want to give some ideas, and I think the main idea is that we prove this using a de Giorgi type iteration argument, but instead of having these level set truncations, we also subtract something time dependent here. Yeah, so we don't only take level sets k, but we also subtract something time dependent, and that is the tail term that we subtract. Yeah, and we subtract the tail term which we integrate in time up to time t. And when you're now an expert on how to prove such estimates, such Kassmann inequalities, well, I told you before that you will always get a tail term in your estimate, but when the time derivative hits this wk, you will not only get the time derivative of u, but you will also get the time derivative of this tail term, yeah, which is just the tail term at time t. Yeah, but you get it with the sign, and the sign kills the tail term that you already have in your Kassmann inequality. Yeah, so we construct it in such a way that there's an automatic cancellation, and then when you run the de Giorgi iteration, you only get the supremum tail here in a slightly larger ball, but not in the complement. Yeah, so in a sense, when you solve your equation in the ball with radius 2r, what was the supremum tail after the cancellation is only the supremum in a ball where you can still solve the equation, where you can still use the solution property. And everything else is cancelled away, and then you only have the L1 tail here because you subtracted it. Okay? And in the region where you solve your equation, you can actually improve from supremum to the L1 norm. Yeah, for this you can use the equation again and iterate. And then you can prove this estimate, which is precisely the one that you want. Okay, so this is the local boundedness estimate. Now, the next question is, what about Hölder regularity? I told you that not every weak solution is Hölder continuous, because there might be solutions that only have finite L1 tail, and then there's the counterexample. And then the question is, okay, what if the tail is not L1 but a little bit better? Well, then we can prove the Hölder estimate, and this is another thing that we do in our paper. So when the tail is in L1 plus epsilon for an arbitrary small epsilon, you still get Hölder continuity. So this is the sharp result in the scale of LP spaces. When epsilon is 0, you have a counterexample. Okay, and then there are a few further developments. So we also proved Ries potential estimates, parabolic Ries potential estimates, together with Hung, with Simon Novak and Yannick Sier. And here we are also able to consider equations with measure data. Yeah? So we also can prove regularity results with right-hand sides, and they can even be measures. And then there are two more recent papers by Bion and Kim, and also by Naian and Liao, and they observed that also for the fractional P Laplacian you can prove something like this. Yeah? This was also not known before, and what Naian also observed, and it's an interesting observation, I think, is that when you only have the tail in L1, then you're not Hölder continuous, that was the counterexample, but you're still continuous. Yeah, you can still, when you track the constants in the oscillation decay, you can see that you are still continuous with the modulus of continuity that depends on the tail. Yeah, but it's not independent of the solution. Okay, so now I told you everything but parabolic Harnack, which is the title of my talk. So now the question is, having these preparations, can we get the parabolic Harnack inequality? And for this, I remind you of this estimate that we proved, right? This local boundedness with the tail term. And now in the elliptic case, as I told you, the main idea is you can control this tail term by the supremum in this ball. Yeah, this was the idea in the elliptic case. Now here, I want to show you again that that's not possible. You cannot do that. Yeah, you need another new idea. And the reason is, well, if you prove this estimate, that this is bounded by the supremum, the argument how to get rid of the supremum was an iteration argument. Yeah, it was an absorption argument. And this made use of the fact that you had a small parameter delta here. And in this case, you cannot have this parameter delta because this is the scaling critical quantity. There's no way to make it small. It will always be there and you cannot make it small. So you need another new idea if you want to get rid of this term for a solution. And actually, Naian proved in a recent paper that, well, what I just said, you cannot put the delta here. There are counterexamples. Okay, so you need another new idea, and the new idea is this estimate, which is an improvement of the weak Harnack inequality. Yeah, I told you on my very first slide that it's known since, I don't know, 2013 that you can bound the L1 norm by the infimum. That's not enough. What you can also do is you can bound the tail term by the infimum. Yeah, so what we prove here is you cannot only bound the tail term by the largest value of the solution inside, but actually by the smallest one. Yeah, so it's a big improvement, not the largest, but the smallest. And well, this was in the elliptic case, you had the supremum. Here we have the infimum, and that's another new ingredient. And this I don't want to tell you how we do it, just the idea you can get it from the non-locality of the energy if you do it in the right way. Yeah, you can use Moser-type test functions. Naian also has an alternative proof using the Georgi class, and I think we've seen it also yesterday in the talk about mixed problems, this kind of estimate, which results from this paper. Okay, so now, once you have this weak Harnack inequality, you're done. Yeah? So what we can prove, and here's the summary, is the actual parabolic Harnack inequality. And what we did was, first we improved this local boundedness estimate, and then we also improved this weak Harnack inequality by being able to put a purely non-local quantity to the left-hand side. Yeah, so it turned out that you need to improve both estimates if you want to prove the Harnack inequality. And now the Harnack inequality is very, very easy to get because there's no absorption argument or anything. Yeah? You just estimate the supremum by this, then you observe that this quantity is on this side, and then you use this estimate, and then you're done. Yeah? It's like in the local case. You just combine the two, no absorption, no nothing, and then you get Harnack like this. Okay, and that's the main result I wanted to explain to you today. Okay, so in the remaining time that I have, I want to go a little bit further and focus on a few more non-local phenomena. Okay, I told you already one of them, and that was that the Hölder regularity fails in the parabolic case, yeah, when you only have these L1 tails. But there are more things about these Harnack inequalities for time-dependent problems that I want to mention and highlight. And one of them deals with a basic application, let's say, of this Harnack inequality, and this deals with heat kernel estimates. Okay, so this is now a linear theory, if you like, but this is a counterpart of a very, very well-known result in the local case, the Aronson type estimates. So what you can do is you can solve this Cauchy problem here in the full space this time, not just in bounded domains, but in the full space, and then you can find the fundamental solution to this equation, right? Which is just the convolution kernel with the initial data. And when you do this convolution, then the function that you get solves the equation. Yeah, and with Naian in a recent paper, we proved that this always exists. This was known already using probability arguments very, very early on, like 15 to 20 years ago, in this very general framework. But we use an analytic proof of this. And then what you can show is that this fundamental solution, it behaves like this function from above and from below. And in the local case, you know that this fundamental solution, it has this Gaussian decay from above and below for the Laplacian. And for every operator in divergence form, they all have the same decay. And this is the so-called Aronson estimates. So in this class, where you have Hölder estimates and you have Harnack, you also have the same behavior of the fundamental solution. And in the non-local case, this is still true. Yeah, but the behavior is a different one. It's this polynomial behavior here, where when x and y get very far apart, then it basically behaves like this weight, like this kernel of the fraction Laplacian. And this was known, as I said, already using probability arguments for kernels that do not depend on t, but using our approach and our Harnack inequality, we can also get it for kernels that depend on t, and it's a purely analytic approach. Yeah? So when you look into the probability papers, they use either very heavily estimates that really have to do with the stochastic process, or they rely very heavily on Dirichlet form theory or semi-group theory. And we can prove here in these two papers actually the upper bound and the lower bound using only these estimates that I showed you on the previous slide. So in this paper here, we prove this upper bound using similar ideas as the ones in Aronson's paper. And I also want to mention very quickly that this lower bound here, we can give with Naian, we can give a very short proof, like half a page of this lower bound, which is very, very basic, and it only relies on this Harnack inequality with this tail term here. Yeah, so what you do is you just use that the fundamental solution is a solution to the equation itself, then you can plug it in this estimate, and then here you have this tail term which already has the decay that you want to get, and then you just estimate the integral in a rather trivial way, and then you can read off the right decay at infinity. So it's a very, very simple argument, and it is new because this weak Harnack was not known, but it gives a very simple proof here, and it's very basic. It doesn't rely on Dirichlet forms or semi-groups. Okay, so why am I telling you this? I want to explain something else now that is again related to Harnack inequalities, and this has to do with this time lag that I mentioned on my very first slide. Okay, so you see in this box, this is a reminder of the Harnack inequality that we prove, right? So you can always bound the supremum by the infimum. This is what we basically showed. But between the interval where you take the supremum and the interval where you take the infimum, there always must be a gap. Yeah? And the gap is basically the difference between this theta 2 and theta 3. And when you let theta 3 and theta 2 go to, the difference go to 0, this constant c, it will explode. Yeah? And this is something that you know very well in the local case. There are very easy counterexamples already by Moser from his 1964 paper. What you do is you just take the fundamental solution, fix it at x0, and then you let x0 go to infinity. And from this Gaussian structure, you will see that your constant, it will depend on x0, and it will explode as x0 goes to infinity if you want Harnack for supremum and infimum at the same time. Yeah, you cannot get this without the time lag. Now, this is very much connected to this Gaussian decay of the fundamental solution. Yeah? And now here, in the non-local case, the fundamental solution decays polynomially, so it decays much slower, and therefore there's much more averaging out. Yeah? And it turns out that actually this function here, it should satisfy this with the same time t. So what Naian and I proved is that actually for non-local equations, parabolic, you can prove a Harnack inequality in the full space where you take the supremum and the infimum over the same time intervals. Okay? So in the non-local case, you do not need this difference between the infimum and the supremum. You just can take the same time interval. So in particular, the supremum here, it can be attained at the right end, at the later end of the interval, and the infimum at the earlier end. So it's really insensitive. It's not on the same slice, but you can also reverse the order of the two. Yeah, and so we cannot only bound the supremum by the infimum, but both of them are controlled by a purely non-local quantity, by a sort of tail term again, at some time here, with the right scale. So the time lag is not needed for these non-local equations, but, and that's the important comment, this is different from what you might know from fast diffusion equations or equations with P Laplacian. The time lag is needed when you solve the equation only in a domain. Yeah? Also in the non-local case. Yeah? So we construct a counterexample in our paper, which shows that you need the time lag if you have it in the bounded domain, but globally you don't need it. What do you mean? The counterexample? Yeah, I agree. I guess the reason is really the behavior of the heat kernel. Yeah, so that it decays polynomially. And in the bounded domain, you can see very easily that you need it because it cannot be time insensitive, right? If you just have boundary data 0 up to a certain time and then different, you cannot change it. Yeah, you have compensation effects because you have the solution property everywhere. Yes, that's the thing. What do you mean? In the global case? Yes. Well, it's not excluded, right? So I mean, so there's a difference here to time 0, right? Maybe that's what answers your question, yeah? So you start at 0 and R here is positive. And yes, yes. Yeah, you need to stay away in a certain sense. Yes? Yes.
It's a harmonic function.
Yes. That was the proof, if you like. Yeah. In the special case, half Laplacian without coefficients. Yes. 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 But this intuition only works without coefficients, right? So, and that's what we prove. Yes. Okay, and what is the idea of the proof? I don't want to spend too much time, just I want to tell you that our argument is purely global, of course. Yeah? So what we prove is, we prove that these weighted L1 norms here, for them you can change the times whatever you like. Yeah? So here, tau and t, they don't need to be ordered. When you prove such an estimate, then on this side you apply this weak Harnack that I showed you, on this side you apply the local boundedness, and then you end up with this. And now I'll show you how we prove this. And we prove it like this. So the idea is very simple. Yeah. So what you do is you take a solution to the dual Cauchy problem. Yeah. Dual means just you put here plus instead of minus. And as the initial data or terminal data, because it's the dual problem, you put this weight. And then what you can show is that the product, the dual pair, the L2 scalar product of u and psi is constant in time. That's what you can prove. And when you know that it's constant in time, you can actually estimate this function psi from above and below, and then you end up with this. Yeah? And to prove that it's constant in time, I mean, the idea is very simple. Yeah? You basically want to test the equation for u with psi and the equation for psi with u. You cannot do it because it's global solutions and they don't have compact support, so you need to cut off. And the cutoff produces like 15 pages of long computations, and you need to use the Harnack inequality again. But basically, this is the idea. Yeah? For making this rigorous. Okay, and then you're done. Yeah, once you have this estimate, then you're done. Okay, and I'm also almost done. I just want to give you a quick summary of what I showed you, and then I want to explain, then I want to end my talk with another non-local effect. Okay, so what I showed you today is that when you have kernels that are comparable to the kernel of the fractional Laplacian in this sense, you solve this parabolic equation, then actually every weak solution is locally bounded. Yeah, this was not known before. We prove every weak solution is locally bounded. Not every weak solution is Hölder continuous. You need something on the tail. That was a non-local thing. You always have parabolic Harnack. So there are solutions that satisfy parabolic Harnack but are not Hölder continuous. I think that's a bit remarkable. And then when omega is the full space, you don't need the time lag. And all of these results, except for the last one, are estimates with constants that do not depend on S. Yeah, we can make all the constants independent of S, so you can send S to 1 and the constants remain bounded. So in a sense, it's really a generalization of the local theory that I just explained. And also, some people are interested in relaxing this lower and upper bound on the kernel, like proving things for kernels that are measures or that are more anisotropic. There might be 0 somewhere, and we can also push this theory a bit further, and we can also generalize these assumptions. Okay, my last slide is an outlook. So what I just explained was the linear case, right? And in the nonlinear case, there are many equations that people considered, and even more than the ones that I listed here. And for most of them, these results, especially the Harnack inequality, is still open. Yeah, so Hölder regularity has been established in most cases, also weak Harnack inequalities, but the actual Harnack inequality is not known. And there are many interesting equations like with fractional P Laplacian or doubly nonlinear, porous medium type equations that you can consider. And now I want to end my talk with a comment on kinetic equations. Okay, I told you that this is a very interesting field because this equation here is really the linearized version of the Boltzmann equation, which is an equation from statistical mechanics. And it is, in a sense, parabolic, but you also have, so it's parabolic in the v direction, in the velocity variable, but you also have this kinetic drift term here. Yeah, and there are very famous, very influential papers by Imbert and Silvestre from the last years, where they develop a de Giorgi-Nash-Moser and a Schauder theory for these equations, and then they're able to apply to the Boltzmann equation and prove some conditional regularity results. And now the natural question after my talk is, of course, can you get Harnack for these ones? Yeah, we have proved it for the parabolic case, we have developed some new techniques, so what about this one? And here it turns out that Harnack is actually false. Yeah, so we have a counterexample in a recent paper where we show that Harnack is false for these kinetic non-local equations, and that's very surprising because it's true in the parabolic case. It's also true in the local case. So local kinetic equations, when you have the Laplacian here, they do satisfy Harnack. In the non-local case, it's false. Yeah, so there's something interesting happening here. So in a sense, I view it like the parabolic case, there the tail terms were already critical. That's the last thing you can do. And when it becomes more general, then they become supercritical and you are basically lost. Okay? So let me end my talk here with the references that my talk was about, and I thank you very much.